On December 14th, 1972, a man climbed a ladder, pulled himself through a hatch, and sealed it behind him. The footprints he left in the dust below are still there, undisturbed, perfectly preserved in a vacuum that has no wind, no rain, no force capable of erasing them. They will still be there in 1,000,000 years. They will still be there in 1,000,000,000. No human being has set foot on the lunar surface since that moment. Not once. Not in over 50 years. We have built the internet, sequenced the human genome, placed a telescope 1.5 million kilometers from Earth. We have done all of it without going back. And here is what most people never stop to ask. The rockets to continue flying already existed. The crews were trained. The missions were planned and scheduled. They were cancelled anyway. The explanation almost everyone reaches for is wrong. What actually happened, what was truly lost, and what returning permanently will demand of us, is a story that reaches further and cuts deeper than any version you have heard before. In this video, we will trace the forces that built Apollo, examine what was deliberately destroyed when it ended, and confront the question that the next 50 years will answer. If this is the kind of story you come here for, subscribing takes a moment, and it genuinely helps this channel reach further. Get comfortable. This one takes a while to fully land. There is a sentence that gets spoken at dinner tables, typed into comment sections, and repeated by people who consider themselves reasonably well informed about the world. 6 words, delivered with total confidence, as though they settle the matter permanently. We have already been to the moon. Say it out loud and listen to what it implies. Already, past tense, completed, checked off the list. The sentence treats the moon the way you might treat a city you visited years ago. Been there, know it, could go back any time if the mood was right. It sounds like a statement of capability. It is actually a statement of assumption. And the assumption is wrong in ways that matter enormously. Here is what the sentence gets right. Between July 1969 and December 1972, 12 human beings walked on the lunar surface across 6 separate landing missions. Neil Armstrong and Buzz Aldrin were the first. Harrison Schmitt and Gene Cernan were the last. In the time between those 2 moments, astronauts collected 842 pounds of rock and soil samples from 6 different sites across the surface. They deployed scientific instruments. They drove an electric rover across the grey dust. They took photographs that became some of the most recognizable images in human history. Gene Cernan, the final man to stand on another world, climbed back into his spacecraft on December 14th, 1972, and that was the end of it. No human being has returned since. Now here is what the sentence gets wrong. It implies that going to the moon once, even 6 times, means that going again should be relatively straightforward. That the engineering was cracked, the puzzle solved, the capability demonstrated and placed neatly on a shelf. That all that stands between us and a return is the collective decision to go. The sentence treats Apollo as a permanent achievement, a technology developed and validated that simply needs to be retrieved and dusted off. The truth is almost precisely the opposite. And understanding why requires dismantling, carefully and completely, everything most people think they know about how Apollo happened in the first place. Think about what Apollo actually produced. 842 pounds of lunar samples, yes. Scientific data from surface experiments, yes. 6 landings, 12 moonwalkers, photographs that will outlast civilization. All of that is real, and none of it is in dispute. But look at what it did not produce. It did not produce a permanent base. It did not establish a supply chain. It did not leave behind any infrastructure capable of supporting the next mission, let alone the one after that. There were no fuel depots waiting in lunar orbit, no habitats anchored to the surface, no technology developed for extracting resources locally. Each mission arrived from Earth carrying everything it would need, used it, and departed. The moon, when the last crew left, was exactly as empty of human capability as it had been before the first crew arrived. Apollo was not a foundation. It was a singularity, a spike of capability produced by conditions so specific, so historically unusual, and so fundamentally unrepeatable that the correct question is not why we stopped going, but how we managed to go at all. That is the story this video is actually about. To understand Apollo, you have to understand fear. Not the polite, managed kind of fear that shows up in risk assessments and probability tables. The acute, visceral, civilization-threatening kind that rewires political priorities overnight and makes normally cautious governments willing to spend almost anything to make a threat go away. On October 4th, 1957, the Soviet Union placed an 83-kilogram aluminium sphere into orbit around the Earth. It was roughly the size of a beach ball. It carried no weapons. It performed no meaningful science. It broadcast a steady radio pulse that anyone with a shortwave receiver could pick up from the ground. Its name was Sputnik, and its effect on the United States was seismic in a way that is genuinely difficult to appreciate from a modern vantage point. America in the late 1950s regarded its technological superiority as a settled matter. This was the country that had built the atomic bomb, industrialized faster than any nation in history, and emerged from the Second World War as the dominant power on Earth. The idea that a rival could outpace American engineering in anything, let alone something as dramatic and visible as putting an object into orbit, had simply not been taken seriously at the highest levels. Sputnik shattered that assumption in a single evening. The response was not measured. Congressional hearings were convened within weeks. Newspapers ran front-page editorials comparing the event to Pearl Harbor. Parents wrote letters to elected officials asking whether their children were safe under a sky now patrolled by Soviet technology. School science curricula were overhauled almost overnight. A national crisis of confidence erupted at every level of American society simultaneously. And the fear was not abstract. This was the deep winter of the Cold War. Both superpowers were building nuclear arsenals at a pace that would seem extraordinary, even by wartime standards. The strategic logic was straightforward and alarming. If the Soviet Union could place an object in orbit, it could place a nuclear warhead anywhere on Earth. Sputnik was not just a satellite. It was a demonstration of intercontinental ballistic missile capability wearing the clothes of peaceful science. The distinction between the two was, at that moment, almost irrelevant. Then it got worse. On April 12th, 1961, a Soviet cosmonaut named Yuri Gagarin became the first human being to leave the atmosphere and orbit the planet. He completed a single orbit in 108 minutes and returned safely. The United States had not yet achieved orbital spaceflight. It watched from the ground. The strategic implications extended far beyond the two superpowers. Across Asia, Africa, and Latin America, nations were choosing sides in the Cold War. Technological achievement had become a proxy for ideological legitimacy, a way of demonstrating to the watching world which system worked. Every Soviet milestone in space sent a message. Communism produces results. The future belongs to Moscow. American prestige, the soft power that underwrote the entire Western alliance, was being eroded in real time. This was the environment in which President John F. Kennedy stood before a joint session of Congress on May 25th, 1961, and committed the United States to landing a man on the moon and returning him safely to the Earth before the decade was out. The speech is remembered today as one of the great declarations of human aspiration. What is less remembered is the calculation behind it. Kennedy was not, by any honest reading of the historical record, a man primarily motivated by wonder at the cosmos. His private correspondence and recorded conversations reveal a leader who understood prestige, understood leverage, and understood that America was losing a contest for global influence on the largest possible stage. He needed a countermove, something dramatic enough and unambiguous enough to reclaim the initiative. Something that could produce a single, undeniable demonstration of American technological supremacy, visible to every nation on Earth simultaneously. Nothing else available. No military program, no economic initiative, no diplomatic maneuver could do that. The moon could. The man who had done more than anyone to make the moon technically plausible was a German-born engineer named Wernher von Braun, who had spent the war designing the V-2 rocket for Nazi Germany and spent the post-war decades building rockets for the United States. His vision of large-scale space exploration predated the political crisis that finally funded it. For von Braun, the moon was always the destination. For Kennedy, it was the instrument. Both men needed each other, and together, they set in motion something that would consume the better part of a decade, 4.5% of the entire federal budget at its peak, and the working lives of more than 400,000 people. Apollo was not born from wonder. It was born from fear. That distinction matters more than almost anything else in this story. There is a way to understand just how extreme Apollo was, and it requires holding one number in your mind for a moment. At its peak in 1966, NASA consumed approximately 4.5% of the entire United States federal budget. Every dollar the federal government spent that year, 4.5 cents of it went to the space agency. Adjusted for today's money and today's spending levels, that figure represents somewhere in the region of $150 billion per year. For context, NASA's current annual budget sits at roughly $25 billion, which itself represents less than half of 1% of federal spending. Apollo-era NASA was receiving, in real terms, 6 times more money than the modern agency. And it was spending it at a pace that had no peacetime parallel, because in every meaningful sense, this was not peacetime. It was a Cold War, and the moon was the battlefield. At the program's height, more than 400,000 people were working on Apollo across roughly 20,000 companies, universities, and government facilities. The supply chain stretched across every state in the Union. Grumman on Long Island built the lunar module. North American Aviation in California built the Command and Service module. Boeing in New Orleans built the first stage of the Saturn V. The scale of the enterprise was unlike anything the country had attempted outside of wartime mobilization, because that is precisely what it was. The working culture inside this machine was extraordinary. 70 and 80-hour weeks were not the exception. They were the expectation. Engineers slept in their offices. Test failures that in any other context would trigger multi-year review processes were analyzed, understood, corrected, and moved past in a matter of weeks. The schedule pressure was not aspirational. It was operational. Kennedy had not said before the end of the decade as an inspiring flourish. He had said it as an instruction. Every decision, every trade study, every design review was measured against that clock. The hardware that emerged from this pressure is staggering even now. The Saturn V rocket, built with Rocketdyne's F-1 engines in its first stage, stood 363 feet tall. Its 5 engines generated 7.5 million pounds of thrust at liftoff, consuming 15 tons of propellant every single second. Nothing built since has matched its raw payload capability. Not the Space Shuttle, not the Falcon Heavy, nothing. The Saturn V remains, by the measure that matters most, the most powerful launch vehicle ever successfully flown. And every one of them was used once. Think about what that means. Each Saturn V was an expendable vehicle. The entire rocket, from the massive first stage to the guidance systems at the top, was flown once and discarded. There was no reuse, no refurbishment, no consideration of long-term economy built into the architecture. Each launch consumed a vehicle that cost, in today's money, somewhere in the region of $1.5 billion. The program burned through 13 of them across the Apollo missions and the Skylab launch. 13 rockets, each one a masterwork of engineering, each one used once and gone. This was not a design failure, it was a design choice. The entire architecture was optimized for one thing, proving it could be done. Getting crews to the lunar surface and bringing them home. Not repeatedly, not economically. Once. Win the contest. Demonstrate the capability. Move on. The lunar module made this philosophy visible in its most extreme form. The vehicle that carried astronauts from lunar orbit to the surface was designed to support 2 people for 72 hours. Its cabin walls measured barely 1/3 of a millimeter thick in some sections, thin enough that pressing too hard with a tool during assembly could risk puncturing the pressure vessel. It was a machine built to the absolute minimum of what was physically necessary, because every gram saved on the lunar module was a gram available for propellant or equipment, and every gram mattered. There was one engine that launched the crew off the surface. One. No backup, no redundant system, no alternative means of returning to lunar orbit if that engine failed to ignite. If it did not fire, the crew would die on the moon. That was the contingency plan. A speechwriter named William Safire prepared remarks for President Nixon to be delivered in the event of crew loss during Apollo 11. The opening line read, "Fate has ordained that the men who went to the moon to explore in peace will stay on the moon to rest in peace." Nixon never had to deliver it, but the fact that it was written and that it was considered a genuine necessity tells you everything about the risk tolerance built into this program. Internal assessments at the time placed the probability of crew loss on any individual mission at somewhere between 1 in 20 and 1 in 10, depending on mission phase. Across the full program, the cumulative probability that at least one crew would be lost was considered significant. The astronauts knew these odds. They were test pilots, men who had built careers around the professional acceptance of risks that most people would find disqualifying. But the broader society accepted those odds too, or at least tolerated them, because the Cold War created a cost-benefit calculation in which the political price of losing the space race was judged to be greater than the human price of losing astronauts. That calculation was never stated so directly in any public speech, but it operated beneath every budget decision, every schedule choice, and every design trade that favored performance over redundancy. Remove it, and the entire architecture of Apollo becomes impossible to justify, which is exactly why nothing like Apollo has been attempted since. To understand what Apollo was, you also have to understand what it was racing against, because the space race only makes sense when you see both sides of it, and the side most people never examine is the one that lost. The Soviet space program in the 1950s and 60s was, in almost every meaningful respect, built around a single human being. His name was Sergei Korolev. He was not a famous man. He could not be. His identity was classified by the Soviet government, his achievements attributed publicly to an anonymous figure known only as the chief designer. Western intelligence agencies spent years trying to identify him. Soviet citizens who followed the space program with enormous national pride had no idea who had made it possible. The most consequential aerospace engineer of the 20th century was, by official decree, a secret. This was not the only extraordinary thing about Korolev's life. In 1938, during Stalin's purges, he was arrested on fabricated charges of sabotaging rocket research and sentenced to 8 years in the Gulag. He spent time in Kolyma, one of the most brutal labor camps in the Soviet system, and came close to dying there. He was eventually transferred to a Sharashka, a prison research institute where technical specialists were put to work under armed guard, and it was in these conditions that he continued his engineering work. He survived. He was rehabilitated after the war, and he went on to design the rockets that launched Sputnik, that carried Yuri Gagarin into orbit, and that were meant to carry Soviet cosmonauts to the moon. The rocket that accomplished the first two of those things was the R-7. It had been designed originally as an intercontinental ballistic missile, a vehicle capable of delivering a nuclear warhead across continents. Its conversion into a space launch vehicle was not a dramatic pivot. It was a natural extension of the same underlying technology. The dual-use logic ran through the entire Soviet program. The rockets that opened space were the same rockets pointed at Western cities. Sputnik's radio signal, so often described as a cheerful beep, was traveling on the same trajectory as a potential warhead. That was never an accident. What Korolev was building toward in the final years of his life was the N-1. This was the Soviet answer to the Saturn V, a massive rocket intended to lift cosmonauts into lunar orbit and send them onto the surface. Where the Saturn V used 5 large engines in its first stage, the N-1 used 30. Where the Saturn V was the product of a vast, well-funded, centrally coordinated industrial machine, the N-1 was built under conditions of chronic underfunding, competing design bureaus, and institutional rivalry that Korolev himself spent enormous energy fighting. He did not live to see it fly. In January 1966, Korolev entered a Moscow hospital for what was expected to be routine surgery. He died on the operating table. He was 59 years old. The Soviet space program, already operating under extraordinary pressure, lost the one figure who had the authority, the technical vision, and the political relationships to hold it together. His successor, Vasily Mishin, inherited a program that was already overstretched and found himself managing it without the personal authority Korolev had spent decades accumulating. The N-1 flew 4 times between 1969 and 1972. All 4 launches ended in catastrophic failure. The third, in June 1971, produced an explosion at the launch pad that was, by some estimates, one of the largest non-nuclear explosions in history. The pad was destroyed. The program was set back by years. By the time the 4th and final test flight failed in November 1972, Apollo had already completed its 6th and last lunar landing. The race, to the extent it had ever been a race in the way Americans understood it, was over. What happened to the Soviet crewed lunar program after that was never officially acknowledged during the Cold War. The program had failed, and the failure was a state secret. Soviet officials publicly denied that there had ever been a competition, claiming the robotic lunar missions had always been the intended approach, that landing cosmonauts on the moon had never been the goal. Privately, the crewed program was quietly wound down. The lunar program itself was real and its achievements were genuine. Luna 9 achieved the first successful soft landing on the moon in February 1966. Luna 16 returned samples to Earth in September 1970. Luna 17 delivered Lunokhod-1, the first robotic rover to operate on the lunar surface, in November of the same year. These were not consolation prizes. They were legitimate firsts. But they were not what the Soviet Union had been trying to achieve, and everyone inside the program knew it. Here is the asymmetry that shaped everything. America needed to win. Winning meant landing astronauts on the moon before the Soviet Union did, on the largest possible stage, in a way that no one could dispute or diminish. Anything short of that was failure. The Soviet Union, by contrast, needed not to lose, which meant that if the crewed program looked likely to fail, the rational response was to quietly abandon it and reframe the entire contest as something the robotic missions had been winning all along. The two positions demanded completely different architectures. America's demanded a sprint to a specific, unambiguous objective at almost any cost. The Soviet Union's demanded flexibility, deniability, and the ability to declare victory on alternative terms. The moment Neil Armstrong stepped onto the lunar surface in July 1969, both of those strategic positions became irrelevant simultaneously. America had won. The Soviet Union had not landed cosmonauts on the moon. The contest was over, and with it, the political emergency that had made Apollo possible evaporated in almost the same instant. On the morning of July 20th, 1969, the most expensive and most urgently funded peacetime program in American history achieved its stated objective. Neil Armstrong's boot pressed into the lunar regolith. The political goal, the one Kennedy had named 8 years earlier, the one that had justified a budget of 4.5% of federal spending, the one that had mobilized 400,000 workers and 20,000 companies, and the collective engineering genius of a generation, was complete. Done. The race was won. America had beaten the Soviet Union to the moon, and every nation on Earth had watched it happen. What occurred next is the part of the story that tends to get skipped over. It happened quietly, without announcement, without drama, and without anything that looked from the outside like a decision of historical consequence. But it was. NASA's budget began falling before Apollo 11 had even returned to Earth. The political consensus that had produced the extraordinary funding of the mid-1960s was not a durable coalition. It had been assembled by fear and sustained by competition. Remove the competition, and the fear had nothing to attach itself to. The moon, as a destination, had never had a natural domestic constituency beyond the crisis that created it. There was no moon lobby, no industrial sector whose survival depended on continued lunar exploration, no strategic interest that required a permanent presence on another world. There was national pride, yes. There was wonder, yes. But wonder does not survive contact with budget committees the way fear does. The mythology of universal public enthusiasm for Apollo does not survive scrutiny. Roger Launius, a historian of the space program who examined polling data from the Apollo era in detail, found a consistent pattern that the triumphant narrative tends to erase. Throughout the program, surveys showed that majorities of Americans believed the money being spent on space exploration was not worth it, that it would be better directed toward problems on Earth. Television ratings for the later Apollo missions dropped sharply compared to the first landing. Apollo 12, 13, and 14 were covered by networks with decreasing investment. By the time Apollo 17 departed for the Moon in December 1972, the last mission, Public Interest, had become a fraction of what it had been 3 years earlier. Apollo had never been popular in the way its mythology suggests. It had been tolerated because the Cold War made the costs seem justified. Once the Cold War rationale evaporated, the tolerance went with it. Richard Nixon understood this. His relationship with Apollo was, by any honest account, instrumental and cool. The program had been Lyndon Johnson's achievement, constructed during the Kennedy administration and carried through on Johnson's political energy. Nixon had no particular attachment to it and no political incentive to fund its continuation. His administration was navigating the Vietnam War, managing the beginning of détente with the Soviet Union, and confronting the domestic turbulence of the late 1960s. The Moon was not a priority. It was an inherited program that had served its purpose. Apollo 18, 19, and 20 were cancelled. Not because the hardware did not exist. The Saturn V rockets were in various stages of production. The crews were trained. The mission plans were written. They were cancelled because Congress would not fund them. The political will had gone. The missions were struck from the manifest without the kind of public debate that their historical significance might have warranted in a series of budget decisions that most Americans barely noticed. Senator Walter Mondale of Minnesota had been arguing for years that the resources consumed by Apollo would be better directed toward education, healthcare, and the needs of the urban poor. His was not a fringe position. It was, the polling data suggests, the majority position, held quietly by a public that had supported the program because of the Cold War and was now relieved to be done with it. By the middle of the 1970s, NASA's budget had contracted to roughly 1% of federal spending, where it has remained, with modest fluctuations, ever since. The drop from 4.5% to 1% was not a temporary adjustment. It was a permanent reorientation, and it meant that whatever came next would have to be done with a fraction of the resources that had made the original achievement possible. The program had not failed. It had succeeded, completely, on its own terms. And in succeeding, it had eliminated the conditions that made it possible. That is a stranger kind of ending than most people expect. It is also the only ending that makes sense. Most people, when they try to explain why humans have not returned to the Moon, eventually land on some version of the same idea. We still have the technology. We know how it was done. If the political will were there, we could go back relatively quickly. The knowledge exists. The blueprints exist. It would just be a matter of resources and commitment. This is one of the most consequential misconceptions in the entire story. What followed Apollo was not a pause. It was not a period of quiet maintenance in which capability was carefully preserved for future use. What followed Apollo was a demolition. And the scale of what was destroyed in the years after the last lunar landing is something that the space program is still reckoning with today. Start with the most visible loss, because it illustrates the rest. The Saturn V production lines did not go into hibernation when the program ended. They were shut down. The specialized tooling built specifically to manufacture the vehicle's components, the jigs that held massive fuel tank sections in alignment during welding, the calibration rigs that verified turbopump clearances, the custom-forming dies that shaped sheet metal into the precise geometries the rocket demanded, was disassembled. In many cases, it was scrapped. The Michoud Assembly Facility in New Orleans, the building where the enormous first-stage propellant tanks had been welded together in a space so vast it generates its own internal weather, was converted to produce external tanks for the space shuttle. The work was different. The infrastructure remained. The purpose was gone. The Rocketdyne facilities that had manufactured the F-1 engine, 5 of which powered the Saturn V's first stage with a combined thrust of £7.5 million, were retooled for other contracts within years of the final Apollo launch. The production capability for the most powerful liquid-fueled rocket engine ever flown dissolved without ceremony. 3 Saturn V rockets survived intact. One lies on its side at the Kennedy Space Center in Florida. A second is displayed at the Johnson Space Center in Houston. A third stands at the U.S. Space and Rocket Center in Huntsville, Alabama. They are extraordinary objects. Standing beneath one produces a physical sense of scale that photographs cannot convey. But they are museum pieces. They are organs removed from a body that no longer exists. You cannot fuel a display exhibit. You cannot launch an artifact. And a single rocket, even a perfect one, is not a space program. A space program is a living system of manufacturing capability, supply chains, engineering expertise, test infrastructure, and institutional knowledge that functions as an integrated whole. The 3 surviving Saturn V rockets are all that remains of something that was, at its peak, the largest and most sophisticated industrial undertaking in peacetime history. The more consequential loss was not the hardware, it was the people. At the program's height, more than 400,000 individuals across the United States were working on Apollo in capacities that ranged from systems engineering to precision machining to quality inspection to materials testing. These were not interchangeable workers performing generic tasks. They were specialists whose expertise had been built over years of direct engagement with problems that existed nowhere else in the world. Consider what it took to weld the cryogenic propellant tanks of a Saturn V. The aluminium-copper alloys used in those structures behaved differently at the temperatures of liquid hydrogen, around -250 degrees Fahrenheit, than they do at room temperature. The welds had to be made to tolerances that left no margin for the thermal stresses the structure would experience during fueling and flight. The technique required to make those welds reliably, the precise torch angle, the travel speed, the feel for how the weld puddle behaved when the alloy approached the edge of its tolerance, could be written down only partially. The rest lived in the hands and instincts of the welders who had done it thousands of times. This is what engineers call tacit knowledge. It is the difference between a specification and the expertise required to meet it. A blueprint can tell you what a component needs to look like when it is finished. It cannot tell you the 10,000 small judgments a skilled machinist makes while producing it. Those judgments are transmitted not through documents, but through proximity, through working alongside someone who has done it correctly so many times that the right way has become instinctive. When Apollo ended, that transmission stopped. The welders moved to shipbuilding and petrochemical work. The machinists who had held tolerances of 10,000ths of an inch on turbopump components moved to automotive and defense manufacturing. The electrical engineers who had designed wiring harnesses containing miles of cable, each connection verified against failure modes that would be fatal at 250,000 miles from Earth, joined the early computer industry. Within 5 years of the last lunar mission, the workforce that had made Apollo physically possible was dispersed across the American economy, its collective expertise diluted beyond recovery. Decades later, when engineers at the Marshall Space Flight Center began revisiting Saturn V documentation as part of studies into new launch vehicle development, they discovered the depth of this loss. Assembly instructions referenced procedures identified only by internal codes that no living engineer could decode. Some instructions contained notes that read simply, "per standard shop practice." In 1966, every technician on the floor knew exactly what that meant. 30 years later, the standard shop practice had walked out the door with the people who had practiced it. The injector plate of the F1 engine is the clearest single illustration of what was lost. That component contained approximately 2,600 individual fuel and oxidizer orifices, each precision drilled and positioned to create the specific spray pattern required for stable combustion at chamber pressures approaching 1,000 pounds per square inch. When engineers later attempted to recreate the component using modern techniques, they found that the underlying physics was understood and the required tolerances were achievable with modern machinery. What was not available was the accumulated process knowledge, which test results indicated an acceptable part, which anomalies were tolerable, which patterns in inspection data signaled an emerging problem before it became a failure. That knowledge had to be reconstructed entirely from scratch. Multiply that challenge across 3 million individual parts, and you begin to understand the true scale of what ended when Apollo ended. What replaced Apollo was not nothing. It was the space shuttle, and the shuttle deserves to be understood for what it actually was, rather than what it was promised to be, because the gap between those two things shaped the next 30 years of American human spaceflight in ways the program has not yet fully recovered from. Nixon approved the shuttle in January 1972. The vehicle that emerged was shaped by forces that had nothing to do with exploration. NASA needed congressional support to survive. The Department of Defense wanted a large cargo bay capable of retrieving satellites from orbit. Budget constraints forced compromises into the design that its original advocates had not intended and could not reverse. The shuttle that flew was the product of negotiation between competing institutional interests. The promises made to justify it were extraordinary: 40 to 50 flights per year, per-flight costs so low that space access would become routine, a system so efficient it would make the expendable rockets of the Apollo era obsolete within years. None of those promises materialized. Across 30 years of operations, the shuttle flew 135 missions, an average of 4.5 flights per year, not 50. The per-flight cost, when all operational expenses were properly accounted for, came to approximately $1.5 billion per mission. Reusability, the feature designed to make the program economical, made it expensive, because refurbishing a vehicle that had survived the violence of launch and the thermal extremes of re-entry required an army of technicians and a level of inspection that the original architects had catastrophically underestimated. The shuttle was not a bad spacecraft. It could carry up to roughly 23 metric tons to low Earth orbit. It supported crews of up to 7. It enabled the assembly of the International Space Station and the servicing of the Hubble Space Telescope. The science conducted across 30 years was real and valuable, but the shuttle had a ceiling. Its maximum operational altitude was approximately 600 kilometers. The Moon is 384,000 kilometers away. The shuttle could no more reach the Moon than a harbor ferry could cross an ocean. And for 3 decades, this vehicle, capable only of low Earth orbit, consumed the overwhelming majority of NASA's human spaceflight budget, engineering attention, and institutional focus. On January 28, 1986, 73 seconds after launch, the Space Shuttle Challenger broke apart over the Atlantic Ocean. The crew of 7 were killed: Francis Scobie, Michael Smith, Judith Resnick, Ellison Onizuka, Ronald McNair, Gregory Jarvis, and Krista McAuliffe, a schoolteacher selected from among 11,000 applicants to fly as a civilian representative. The Presidential Commission found that the cause was a failed O-ring seal in one of the solid rocket boosters, and that engineering concerns about the seal's performance in cold temperatures had been raised before the launch and dismissed. The fleet was grounded for 32 months. 17 years later, on February 1st, 2003, Columbia disintegrated during re-entry, killing all 7 crew members. A piece of foam insulation had struck the wing's thermal protection during launch. The Columbia Accident Investigation Board found that the physical cause was the foam strike, and that the organizational cause was a culture in which known risks had been normalized and engineering dissent had been systematically marginalized. The fleet was grounded for over 2 years. These responses were correct. They reflected a mature recognition that human lives are not expendable in the service of schedules. But they also reveal, in the starkest possible terms, why the Apollo risk tolerance could never be reconstructed. A crew loss under Apollo was a tragedy the program absorbed and continued through. A crew loss under the shuttle reshaped the entire institution for years. The difference was not callousness in one era and sensitivity in another. The difference was that Apollo operated under conditions in which the political cost of not succeeding was judged to exceed the human cost of failure. Those conditions have not existed since. The shuttle was retired in July 2011. In the 30 years it operated, it spent roughly $200 billion inflation-adjusted dollars, achieving a maximum altitude of 600 kilometers. In that same period, not a single human being traveled beyond low Earth orbit. Not once. While the shuttle was consuming 3 decades of NASA's human spaceflight resources in low Earth orbit, something else was being built. Something that would, in time, become the most important data source available to anyone planning a return to deep space. It is also the most vivid illustration of the paradox that has defined the post-Apollo era. Humanity's most sustained achievement in human spaceflight has been conducted at an altitude a well-aimed aircraft could theoretically reach. The International Space Station has been continuously inhabited since November 2nd, 2000. That is over 2 decades of unbroken human presence in space, across 5 American presidential administrations, 1 catastrophic shuttle accident, the end of the shuttle program itself, and geopolitical tensions between partner nations that in any other context would have ended the collaboration entirely. It is, by that measure alone, one of the most remarkable institutional achievements in the history of spaceflight. It is also, measured in distance from the lunar surface, approximately 380,000 kilometers away from where humans need to go next. The station orbits at roughly 400 kilometers above the Earth. The Moon sits nearly 1,000 times further away. For all the extraordinary science conducted aboard it, for all the engineering sophistication it represents, the station has never brought humanity 1 meter closer to the lunar surface. And for the 2 decades it has been operating, it has absorbed the budget, the engineering talent, and the institutional attention that might otherwise have been directed toward the capability gap that matters most. Hold both of those truths at once, because both are true. The station is a genuine marvel. It is also a genuine drain on deep space ambition. What it has produced, and this does matter for the story ahead, is the most comprehensive dataset on long-duration human spaceflight in history. Every crew member who has lived aboard the station has returned with a body changed by the experience. Bone mineral density decreases at a rate of roughly 1 to 2% per month in the early years of the program, before countermeasure exercise protocols were developed and refined. Muscle mass declines. The cardiovascular system adapts to the absence of gravitational loading in ways that require months of rehabilitation after landing. The immune system is suppressed. Intracranial pressure increases, producing visual impairment in a significant proportion of long-duration crew members, an effect that was not well understood for years and whose long-term consequences remain under active study. Scott Kelly spent 340 days aboard the station between 2015 and 2016, the longest single American spaceflight at the time, as part of a deliberate study of what extended exposure to microgravity does to a human body. His identical twin brother, Mark Kelly, remained on Earth as a control subject. The comparison between them, documented in detail by NASA researchers, revealed changes in gene expression, gut microbiome composition, cognitive performance, and vascular structure that had not been fully anticipated. Some changes reversed after Scott returned to Earth. Others did not. This data is essential for planning any future deep space mission, and it is simultaneously insufficient for a reason that cuts directly to the challenge of lunar habitation. The station operates in microgravity, the effective weightlessness of continuous orbital freefall. The Moon has gravity, not Earth gravity, but real gravity, approximately 1/6 of what you experience standing on the surface here. No one has lived in 1/6 gravity for an extended period. No one has studied what it does to the human body over weeks or months. The station tells us what zero gravity does. It tells us almost nothing about what lunar gravity does. That is a knowledge gap that will only close when humans are actually living on the moon, which is one of the reasons going there matters beyond the symbolic. Shannon Lucid had set American records for long-duration spaceflight before the station existed, aboard the Russian Mir space station in the 1990s. The data her missions generated fed into the planning for the station itself. That cumulative, generational build-up of knowledge is how the field moves forward. But it moves forward slowly, and it requires continuous presence, continuous investment, and continuous commitment. All three have been harder to sustain than anyone in the early program years anticipated. The combined effect of the shuttle program and the station is straightforward to state and uncomfortable to sit with. For roughly 30 years, from the shuttle's first flight in April 1981 to its retirement in July 2011, NASA's human spaceflight program was defined almost entirely by two objectives: flying the shuttle and building and maintaining the station. Both were genuine achievements. Neither moved a human being 1 kilometer closer to the moon. There is a structural problem at the heart of every attempt to return humans to the moon, and it is not an engineering problem. It has nothing to do with rocket propulsion or life support or radiation shielding. It is a problem of institutional time, and it has defeated every serious attempt at lunar return since Apollo ended. Developing a human-rated deep space transportation system from initial concept through design, manufacture, testing, and operational certification takes between 10 and 15 years under favorable conditions. This is not a pessimistic estimate. It is the observed historical record across multiple programs in multiple countries. The shuttle took approximately 9 years from program approval to first flight. The International Space Station took over a decade from initial international agreement to the launch of its first module. The Space Launch System, which drew heavily on existing shuttle heritage hardware and components, took over 12 years from formal authorization to its first flight. The Orion capsule has been in continuous development for nearly 20 years. These timescales are not the product of incompetence, though incompetence exists in any large organization. They reflect the genuine complexity of designing, building, testing, and certifying systems that must function with extreme reliability in environments that would destroy most human-made objects. You cannot meaningfully compress that process without accepting risks that modern safety standards prohibit. And modern safety standards exist because of Challenger, because of Columbia, because of the hard-won understanding that the consequences of cutting corners in human spaceflight are paid for in lives. Now place that technical timeline against the political one. An American president serves a maximum of 8 years. Congressional terms run 2 years for the House and 6 for the Senate. The federal budget is authorized annually, with no binding mechanism to commit future Congresses to multi-year spending plans. Each new administration arrives with its own priorities, its own appointed NASA leadership, and its own political calculation about what is worth funding. A program that requires 25 years of sustained investment must survive at minimum 3 and possibly 4 changes of presidential administration. Not one post-Apollo lunar program has managed it. George H.W. Bush stood on the steps of the National Air and Space Museum on the 20th anniversary of Apollo 11's landing, July the 20th, 1989, and called for a permanent return to the Moon and human missions to Mars. NASA produced a planning document, known informally as the 90-day report, that laid out an architecture requiring an estimated $500 billion over 20 to 30 years. Congress recoiled from the price. The initiative was functionally dead within 2 years, replaced by the budget realities of an agency that had nowhere near the resources to execute it. George W. Bush announced the vision for space exploration in January 2004. The program that resulted, Constellation, was the most concrete attempt at lunar return since Apollo itself. Real engineering work was done. The Ares 1 crew launch vehicle, the Ares 5 heavy-lift cargo rocket, the Orion crew capsule, the Altair lunar lander. These were not political promises. They were hardware programs with teams of engineers working on them, cutting metal, running tests, solving problems. Orion underwent significant development. Ares 1 progressed to a test flight. Progress was made, but the program was chronically underfunded relative to what its ambitions required. Schedules slipped, costs grew. In 2009, a review panel led by Norman Augustine, a former chief executive of Lockheed Martin, with deep experience in large-scale aerospace programs, concluded that Constellation's goals were not executable within projected budget profiles. The panel was explicit. The problem was not technical feasibility. The engineering was sound. The problem was that the program had been given objectives requiring Apollo-scale resources and provided with a fraction of Apollo-scale funding. In 2010, the Obama administration cancelled Constellation. Ares 1 was terminated. The Altair lander was cancelled. Billions of dollars in development work was archived. Orion survived, eventually becoming part of the Artemis architecture, but the program as a coherent whole was gone. Think about what that cancellation meant for the people inside it. Engineers who had uprooted their families and moved to Huntsville or Houston, or the Kennedy Space Center, for the specific purpose of building the next generation of deep space vehicles, found themselves reassigned to programs with uncertain futures, or let go entirely. Specialists who had spent 4 or 5 years developing deep expertise in specific systems, in the throttleable descent engine of the Altair lander, in the Earth departure stage of the Ares 5, in the thermal protection architecture of a vehicle designed to return from lunar distances, discovered that their hard-won knowledge had no immediate application elsewhere. Some found work in the commercial space sector, which was beginning to emerge as a genuine industry. Others left aerospace entirely. This is the institutional damage that accumulates across cycles of initiation and cancellation, and it is harder to quantify than hardware costs, and therefore easier to ignore. Each cancellation does not merely waste the money spent. It disperses teams that took years to assemble. It extinguishes expertise that cannot be quickly reconstructed. It teaches the next generation of engineers, the ones watching from the outside as they decide what to do with their careers, that deep space programs start and stop, and that committing fully to one is a reasonable way to find yourself stranded. By the time the Artemis program was formally established, the aerospace workforce had been shaped by decades of exactly this pattern. The institutional memory of a program that started, made genuine progress, and ran to completion in human deep space exploration did not exist for anyone who had entered the field after Apollo. That absence is not a detail. It is the context in which everything that follows has to happen. There is a second misconception layered beneath the first, and it does at least as much damage to public understanding of why lunar return has taken so long. The first misconception, as we have seen, is that Apollo left behind a preserved capability waiting to be reactivated. The second is subtler and in some ways more insidious. It goes like this. We went to the moon in 1969 with computers less powerful than a modern wristwatch. We had no sophisticated simulation tools, no digital design systems, no carbon fiber composites, no advanced manufacturing techniques. Surely with everything we have now, going back should be easier, not harder. Technological progress moves in one direction. We should be better at this than we were 50 years ago. This reasoning feels airtight. The part it misses is that the reasoning assumes we are trying to solve the same problem. We are not. Apollo and modern lunar return share a destination. They share almost nothing else. The mission that Apollo was designed to accomplish, and the mission that any serious return program must accomplish, are separated not by degree, but by kind. Understanding that distinction is the key to understanding why the timeline ahead is measured in years and decades rather than months. Apollo was built around one governing principle: minimum time on target. Get to the surface, perform activities, get off the surface, come home. Every system aboard every spacecraft was sized to support that objective and nothing beyond it. The 6 landing missions put crews on the lunar surface for periods ranging from 21 hours to just over 75 hours. The longest single stay, during Apollo 17, lasted 3 days. Transit time from Earth to lunar orbit was approximately 3 days each way. Total mission duration from launch to splashdown ranged from 8 to 12 days. Every consumable, every power reserve, every structural margin was calibrated to that timeline with minimal excess. This was not a limitation to be apologized for. It was the correct engineering response to the mission as defined. You design for what you need. Apollo needed brief visits. It was exquisitely designed for brief visits. But here is what brief visits do not require. They do not require habitats capable of sheltering crews across multiple weeks of temperature extremes. They do not require power systems capable of operating through 2 weeks of continuous darkness. They do not require closed-loop life support systems that recycle air and water indefinitely rather than consuming and discarding them. They do not require radiation shelters or dust management systems designed for months of continuous surface operations or in-situ resource extraction capability. None of those things were needed, so none of them were developed. The Moon itself has not changed. The challenges of operating there across extended periods were present in 1969. Apollo simply scheduled around them with an elegance that is worth examining. The Moon rotates once every 29.5 Earth days. This means the lunar surface experiences approximately 14 days of continuous sunlight, followed by approximately 14 days of complete darkness. During the sunlit period, temperatures at equatorial latitudes climb to around 120 degrees Celsius. During the dark period, they fall to around -170 degrees. That swing of nearly 300 degrees occurs across every lunar day-night cycle, every month, without variation or mercy. Apollo avoided this entirely. Every landing mission touched down during lunar morning at carefully chosen equatorial sites, when the sun was low enough on the horizon that surface temperatures were moderate, and shadows were long enough to be useful for reading terrain. Crews were never on the surface long enough for the thermal environment to shift significantly. The lunar module's thermal control systems were designed for a narrow temperature range and a short operational period. They did not have to handle the extremes of the full day-night cycle because they were never exposed to them. Sustained presence cannot use that scheduling trick. An outpost that operates continuously must operate through the lunar night. It must function at -170 degrees and at 120 degrees and at every temperature between them. Equipment must survive repeated thermal cycling across that full range. Materials expand and contract. Seals fatigue. Lubricants that perform reliably at one extreme may fail at the other. Engineering for that environment is a fundamentally different challenge from engineering for a 3-day visit during the most benign part of the cycle. The lunar poles offer a partial resolution to this problem, and it comes from an unexpected direction: geometry. The Moon's axial tilt is only 1.5 degrees from the plane of its orbit around the Sun. This is extraordinarily small compared to Earth's 23.5 degrees. The practical consequence is that elevated terrain near the lunar poles can remain in near-continuous sunlight throughout the entire year. Crater rims and mountain peaks near the South Pole, locations that Paul Spudis and others spent years advocating for as the foundation of any serious lunar architecture, receive illumination for roughly 90% of the lunar year at the most favorable sites. The geometry that makes most of the Moon brutally inhospitable to sustained operations becomes, near the poles, an engineering asset. These are not hypothetical locations. The Lunar Reconnaissance Orbiter has mapped them in detail. The rim of Shackleton Crater, the Malapert Massif, and several other elevated positions near the South Pole have been characterized with sufficient precision to identify candidate landing zones and outpost sites. A solar array positioned on one of these peaks can generate electricity through the long lunar night that would leave an equatorial outpost completely without power. The thermal environment, while still challenging, is far less extreme than at lower latitudes, and immediately adjacent to these sunlit peaks, separated in some cases by distances measurable in kilometers, are some of the coldest and most scientifically significant places in the entire inner solar system. The permanently shadowed craters near the lunar South Pole have not seen direct sunlight in billions of years. Their floors sit in perpetual darkness, shielded by crater walls that block every angle of solar illumination as the moon slowly orbits the sun. In those depths, temperatures fall to around -230 degrees Celsius, colder than the surface of Pluto. Cold enough to preserve, essentially indefinitely, volatile compounds that would have evaporated long ago anywhere else on the moon. On October the 9th, 2009, a Centaur rocket stage traveling at approximately 2.5 kilometers per second impacted into one of those craters. The crater was Cabeus, located near the lunar South Pole. The impact was deliberate. It was the terminal phase of the Lunar Crater Observation and Sensing Satellite mission, known as LCROSS. A shepherding spacecraft followed 4 minutes behind the impactor, flying through the ejector plume the impact had thrown up and analyzing its composition before itself hitting the surface. Additional instruments on the Lunar Reconnaissance Orbiter observed from above. The analysis, led by Anthony Colaprete at the NASA Ames Research Center and published in Science in 2010, confirmed what orbital data had suggested but never definitively proven. Water ice was present in the Cabeus crater at concentrations of approximately 5.6% by mass. The plume also contained carbon dioxide, carbon monoxide, methane, ammonia, and hydrogen sulfide. The cold trap at the bottom of that permanently shadowed crater had been accumulating volatile compounds delivered by cometary impacts and implanted by the solar wind across geological time. It had been holding them, undisturbed, for billions of years. Water ice on the moon is not merely scientifically interesting. It changes the economic architecture of deep space exploration in a way that is difficult to overstate. Consider the problem of propellant. Every kilogram of material launched from Earth's surface to low Earth orbit costs thousands of dollars under the best current pricing. Getting that kilogram to the lunar surface costs significantly more. The deep space missions of the coming decades, crewed flights to the moon and eventually to Mars, require enormous quantities of propellant. Carrying all of it from Earth is not just expensive. At the scale required for sustained operations, it approaches the prohibitive. Water, however, can be split into hydrogen and oxygen through electrolysis, the application of electrical current to liquid water. Hydrogen and oxygen are rocket propellants. They are, in fact, among the most energetically efficient propellants available. The space shuttle's main engines ran on them. If water ice can be extracted from the moon's polar craters and processed into propellant on the surface, the economics of cislunar and deep space operations shift fundamentally. The moon stops being a destination that must be supplied entirely from Earth and starts being a resource base that can sustain missions departing for further destinations without the crushing weight of carrying every kilogram of propellant from the bottom of Earth's gravity well. This concept is called in situ resource utilization. It has been discussed in planning documents and academic papers for decades. Translating it from concept to operational reality requires solving problems that are genuinely difficult. Extracting water ice from permanently shadowed craters at -230 degrees Celsius is not a straightforward mining operation. Equipment operating in permanent darkness at those temperatures faces material challenges that conventional engineering was not designed to address. Most lubricants cease to function. Standard seals become brittle. Electronics require thermal management systems that add complexity and mass. The excavated regolith containing ice must be transported to processing equipment where carefully controlled heat is applied to sublimate the ice, converting it directly from solid to vapor, which is then captured, cooled, and processed. The entire chain requires reliable power delivered to locations that receive no sunlight. Robotic missions are being designed specifically to characterize what is actually down there before crews arrive. NASA's Volatiles. Investigating Polar Exploration Rover, known as Viper, is intended to traverse the South Polar region, enter the margins of permanently shadowed craters, and map water ice distribution at a resolution that orbital data cannot provide. A joint mission between the Japan Aerospace Exploration Agency and the Indian Space Research Organization, called LUPEX, is designed to drill into the regolith to confirm ice presence at depth rather than just at the surface. The data from those missions will determine where extraction equipment should be placed, how deep the ice-bearing layers lie, what concentration and form the ice takes, and what the regolith properties mean for the engineering of excavation systems. Until that data exists, the architecture of an operational resource extraction system cannot be finalized. And until the architecture is finalized, the hardware cannot be built. And until the hardware is built and tested and validated in the actual environment, the economic transformation that water ice makes possible remains a promise rather than a capability. The gap between the L-Cross conformation and operational propellant production on the Moon is not a gap that closes quickly. It closes through the patient, sequential accumulation of knowledge and hardware that is the only way complex engineering problems in genuinely hostile environments ever get solved. That process is underway. It is not fast, and its pace is shaped, as it has always been, as much by the resources directed toward it as by the difficulty of the problems themselves. Every system that keeps human beings alive on the lunar surface belongs to a category of engineering that Apollo barely had to think about. Not because the problems were not real in 1969, but because the missions were short enough that the simplest possible solutions worked. Carry what you need, use it, come home. When that logic breaks down, which it does the moment missions extend from days to weeks, an entirely different generation of technology has to take its place. Life support is where the difference becomes most visible. Apollo used what engineers call open-loop systems. Oxygen was stored in high-pressure tanks and released into the cabin as needed. Carbon dioxide exhaled by the crew was managed by passing cabin air through canisters filled with lithium hydroxide, a chemical that absorbs carbon dioxide through an irreversible reaction. Once a canister was saturated, it was set aside and a fresh one installed. Water was generated as a byproduct of the fuel cells that produced the spacecraft's electrical power. Food came pre-packaged. Waste was collected and stored. The entire system was simple, reliable, and well understood. For missions lasting days, it worked elegantly. Now extend that logic. Take a crew of 4 and give them a surface mission lasting 28 days. The oxygen requirement scales with crew size and duration. The lithium hydroxide canister requirement scales the same way. Water consumption for drinking, food preparation, basic hygiene, and equipment cooling scales proportionally. Food mass increases. Waste storage volume increases. The total consumable mass required to sustain that crew for a month using Apollo-style open-loop life support would exceed the entire payload capacity of the lunar module by a margin that makes the approach unworkable. You cannot carry enough supplies for a month-long expedition using systems designed for a 3-day camping trip. The arithmetic defeats you before you leave the launch pad. The solution is to stop treating consumables as single-use. Closed-loop life support systems recycle rather than discard. The International Space Station has operated such systems for over 2 decades, and in their mature form, they are genuinely impressive. The water recovery system on the station processes humidity condensate from the cabin atmosphere, urine from the crew, and other wastewater streams through a series of treatment stages that include distillation, catalytic oxidation, ion exchange, and filtration, ultimately producing water of sufficient purity to drink. With the addition of a brine processor assembly that extracts water from the concentrated waste stream that earlier versions could not fully treat, the system now recovers approximately 98% of the water entering it. For every 100 kilograms of water the crew would otherwise need to have delivered from Earth, the system recovers 98 kilograms from materials already aboard. Oxygen generation works through electrolysis. Electrical current passed through water splits it into hydrogen and oxygen, with the oxygen released into the cabin atmosphere and the hydrogen either vented or used in other processes. Carbon dioxide is removed not by disposable canisters, but by regenerable molecular sieve beds that adsorb carbon dioxide on one cycle and release it on the next when heated, a process that can be repeated thousands of times before the sorbent material needs replacement. These systems work. Their operational record on the station is the proof. but their operational record also includes pump failures, contamination events, sensor malfunctions, a sensor module that had to be replaced multiple times, and periods during which backup systems were carrying the load while the primary system was under repair. Every one of those failures was managed without a crisis, because resupply vehicles can reach the station within days to weeks, because spare components can be delivered on relatively short notice, and because the station's orbit keeps it within reach of emergency intervention if the situation deteriorates seriously. On the lunar surface, that safety net disappears. A resupply mission from Earth requires a dedicated launch, a transit of approximately 3 days each way, and a landing. From the moment a critical life support component fails, the crew has whatever reserves the habitat carries and whatever time the repair can be completed within. If the carbon dioxide removal system fails and the repair requires a part that is not aboard, the crew is not waiting a few days for a delivery. They are waiting weeks at minimum, in a sealed volume where carbon dioxide concentration will climb steadily until it reaches levels that impair cognition and eventually become dangerous. This drives every closed-loop life support design for lunar surface use toward redundancy, toward spare component inventories, toward backup system architectures that add mass and complexity in exchange for the margins that remote operations require. And it drives designers toward a further complication that the station's engineers never had to solve in the same way. The station operates in microgravity. Many of the fluid separation processes in water recovery systems rely on gravity-driven phase separation, on the natural tendency of liquids to settle and gases to rise. In 1/6 gravity, those processes behave differently. Systems validated in microgravity on the station are not automatically validated for the lunar surface. Each one requires analysis, adaptation, and testing in the actual gravitational environment before it can be trusted with crew safety. The carbon dioxide partial pressure in a sealed habitat, the narrow band between the comfortable range and the level that begins to impair performance, must be managed with consistency that depends on systems functioning correctly in an environment where gravity is real but weak, and where the interaction of that gravity with fluid dynamics in life support hardware has not been studied in operational conditions. None of this is unsolvable. The problems are difficult, not intractable, but they require the patient work of development, testing, qualification, and operational experience that cannot be shortcut without accepting risks that the post-Apollo era has decided are unacceptable. That work is underway. It is being done carefully, and it will take the time it takes. Somewhere above the lunar South Pole at this moment, radiation is falling. Not dramatically, not in a way you could see or hear or feel. It arrives from every direction simultaneously, a continuous rain of particles that has been falling on the moon since long before life existed on Earth, and it will still be falling long after every human mission we can currently conceive of has come and gone. The moon has no global magnetic field. Earth's magnetic field, the vast invisible structure generated by the planet's molten iron core, deflects the most energetic charged particles flowing outward from the Sun and shields the surface from a significant fraction of the radiation present in interplanetary space. The moon has no equivalent. Its surface is exposed, without meaningful shielding of any kind, to the full spectrum of what space offers. That spectrum has two main components, and they present different kinds of problems. Galactic cosmic rays are high-energy particles that originate from supernovae, neutron star mergers, and other violent events distributed throughout the galaxy. They arrive from all directions, at all times, at energies so extreme that individual particles can carry the kinetic energy of a professionally thrown baseball concentrated into a single atomic nucleus. They penetrate conventional shielding materials readily. Some, when they strike shielding, generate secondary radiation showers that can actually increase the dose received by crew members behind thin barriers rather than decreasing it. Effective shielding against galactic cosmic rays requires substantial mass, several meters of regolith piled above a habitat, or thick layers of hydrogen-rich materials such as water or polyethylene, both of which have the advantage of absorbing energy from the incoming particles rather than generating secondary cascades. Galactic cosmic ray exposure accumulates steadily over time. A crew on the lunar surface for 3 days receives a dose. A crew on the surface for 30 days receives roughly 10 times that dose. A rotating crew presence across a full year of operations receives a dose that begins to approach or exceed the career limits that NASA's radiation medical standards are designed to protect. Those limits exist because the biological consequences of ionizing radiation exposure, elevated cancer risk, increased probability of cardiovascular disease, potential cognitive effects from high-energy particle strikes to brain tissue, are real and quantifiable. They are not hypothetical risks dismissed by subsequent science. They are the reason modern spaceflight programs take radiation exposure seriously in a way that Apollo, with its brief missions, did not have to. Solar particle events are different in character and in some respects more immediately dangerous. These are intense bursts of energetic protons ejected from the sun during coronal mass ejections and solar flares. They are unpredictable. They can occur with little warning, sometimes as little as 15 to 30 minutes between the first observable signs on the sun and the arrival of the particle front at the moon's distance. Their intensity varies enormously. Minor events deliver doses that are manageable inconveniences. Major events deliver doses capable of causing acute radiation syndrome, nausea, vomiting, immune suppression, increased cancer risk, and in the most severe cases, effects that could become life-threatening without medical intervention. The Apollo program survived 6 lunar surface missions without encountering a major solar particle event during any of them. This was not guaranteed. In August of 1972, between the Apollo 16 and Apollo 17 missions, a solar proton event of considerable intensity occurred. Lawrence Townsend, a radiation physicist at the University of Tennessee who has studied the event in detail, estimated that a crew on the lunar surface during that storm would have received a dose of several hundred millisieverts over a matter of hours, enough to cause acute symptoms and significantly elevate lifetime cancer risk. Whether it would have been immediately life-threatening is debated. That it would have constituted a serious medical emergency is not. For a program flying 6 short missions, the statistical probability of coinciding with a major event was low enough to accept. For a sustained presence with crews rotating through the South Pole continuously over months and years, the probability of encountering at least one significant event is not a minor risk factor. It is a near certainty over the lifetime of the program. Modern lunar habitat designs must therefore treat radiation protection as a primary constraint rather than a secondary consideration. Habitats need shielding sufficient to meaningfully reduce galactic cosmic ray exposure, most likely achieved by piling several meters of regolith over the structure, which requires the habitat to be structurally robust enough to bear that load. Every pressurized volume needs a dedicated storm shelter, a smaller space within the habitat with enhanced shielding, accessible within the warning window available for a solar event, stocked with enough food, water, and carbon dioxide scrubbing capacity to sustain the crew for at least 24 to 72 hours until the storm passes. Continuous radiation monitoring and early warning systems linked to solar observation networks watching the sun from multiple angles must be in place and functioning reliably before the first crew member steps onto the surface. Apollo's architecture was never designed to meet any of these requirements. It did not need to be. The sprint that Apollo was designed to execute and the sustained presence that modern programs are designed to establish are not the same mission. They are not even close. There is one more hazard that Apollo encountered, documented carefully, and then never had to truly manage. It was present on every mission. It got inside every spacecraft. It irritated eyes, abraded surfaces, clogged mechanisms, and coated every piece of equipment that came into contact with the lunar surface. The Apollo astronauts mentioned it constantly in debriefs, and because every mission lasted only days, it was treated as a nuisance rather than the serious engineering and health challenge it becomes the moment missions extend to months. Lunar regolith is not like sand. The comparison to sand is the natural one to reach for, and it is wrong in ways that matter. Sand on Earth has been shaped by billions of years of wind and water erosion. The particles are rounded, their edges smoothed by constant physical contact with other particles and with fluid flows. They are mechanically gentle. Lunar regolith has experienced none of that. The surface of the Moon has been bombarded by micrometeorites for 4.5 billion years, in an environment with no atmosphere to slow them and no water to soften the impacts. Each collision shatters surface material into fragments. Those fragments are never rounded, never softened. They are jagged shards of glass and mineral with edges that remain sharp essentially forever, because there is no mechanism on the Moon capable of wearing them down. The particles are also electrostatically charged. Solar ultraviolet radiation and the solar wind, the continuous flow of charged particles from the Sun, interact with the lunar surface to impart persistent electrostatic charges to regolith particles. This causes them to cling tenaciously to almost any surface they touch. They adhere to spacesuit fabric. They coat visor surfaces and degrade optical clarity. They accumulate on thermal radiators and reduce their efficiency. They settle on solar array surfaces and reduce power output. They infiltrate every gap and seal and joint they can find. Harrison Schmitt noticed it in the most direct possible way. Schmitt was the geologist on Apollo 17, the only professional scientist to walk on the Moon during the entire Apollo program, and he reported after the mission that exposure to dust that had been tracked into the lunar module cabin produced symptoms he described as resembling hay fever, nasal congestion, irritation of the eyes and throat, effects that persisted for hours after the surface excursion ended. This was not a trivial observation. It was the first documented case of an acute human physiological response to lunar regolith inhalation, experienced after a single brief exposure during a 3-day mission. The respiratory concern at longer exposures is taken seriously by researchers studying the health implications of extended lunar surface operations. Lunar regolith contains a significant fraction of nanoscale particles, including silicate shards at sizes capable of penetrating deep into lung tissue. The terrestrial analogy that researchers reach for is silicosis, the lung disease caused by chronic inhalation of fine crystalline silica dust, which has historically been a serious occupational health hazard in mining, stone cutting, and sandblasting. The specific toxicology of lunar regolith at the exposures that a crew member living on the Moon for weeks or months might accumulate has never been studied in any direct way. The data simply does not exist. It cannot exist until people have spent significant time in that environment, which requires first solving the problem well enough to get them there safely. The mechanical hazard runs in parallel with the health one. Abrasive particles accelerating wear on spacesuit joint bearings, on seals, on the mechanisms that allow suited crew members to move freely, do so at rates that 3-day Apollo missions never had time to reveal. A suit bearing that shows no measurable degradation after 20 hours of surface operation might show significant degradation after 200 hours. The question of how a suit designed for hundreds of hours of total use degrades under continuous exposure to regolith over the weeks and months of a sustained mission is an open engineering question that cannot be answered by analysis alone. It requires testing in conditions that closely replicate the actual environment, and it requires honest accounting for what happens when degradation is found. Brian O'Brien, an Australian physicist who designed the dust detector experiments flown on the Apollo 11, 12, 14, and 15 missions, spent years after the program working with the data those instruments collected and advocating for serious engineering attention to the dust problem. His instruments measured how regolith accumulated on exposed surfaces over time and how electrostatic effects varied across the lunar day. The data showed patterns of dust accumulation and redistribution that were more dynamic and more variable than mission planners had assumed. The problem, his work consistently indicated, was worse than the brief Apollo surface stays had made it appear. Managing dust for extended surface operations requires an approach that Apollo never needed. Suitport systems, in which a spacesuit is mounted to the exterior of the habitat and an astronaut enters it from inside without ever bringing the suit's exterior surfaces into the pressurized volume, prevent the single largest source of dust ingress into the habitat. Electrostatic dust removal systems, which use electric fields to lift charged particles off surfaces, are under development at the NASA Glenn Research Center as a way of cleaning suit surfaces and optical instruments without physical contact that would grind abrasive particles into protective coatings. Active airlock designs with cleaning cycles, dust-resistant material coatings, and continuous filtration of habitat air are all components of a dust management architecture that must be integrated into every surface system from the earliest design stages. Every Apollo surface system was engineered to tolerate dust for days. Every modern surface system must be engineered to resist it for months. These are not the same design problem. Power sits underneath every other challenge on the lunar surface. Without power, life support fails. Without power, thermal management fails. Without power, communications fail, science stops, resource processing stops, and the habitat becomes a sealed box in which people can survive only as long as their stored reserves hold out. Power is not one challenge among many. It is the precondition for everything else. At equatorial sites, the power generation problem presents itself in its most brutal form. Solar arrays produce electricity when sunlight strikes them. During the 14-day lunar night, no sunlight strikes them. For 2 weeks out of every 4, a solar-powered equatorial outpost generates no electricity at all. Bridging that gap with batteries is theoretically possible. In practice, the energy required to sustain even a minimal life support system, thermal management network, and communications capability through 14 days of darkness would demand battery storage systems so massive that their launch cost alone would represent a significant fraction of the program's total budget. Current battery technology simply cannot close the gap at a mass and cost that makes an equatorial outpost viable. The south polar peaks of eternal light resolve the power generation problem through geometry rather than technology. Because the moon's axial tilt is only 1.5 degrees, elevated terrain near the poles can remain in near continuous sunlight as the moon orbits the sun. The rim of Shackleton Crater, the Malapert Massif, and several other elevated positions identified through detailed lunar reconnaissance orbiter mapping receive solar illumination for roughly 90% of the lunar year at the most favorable locations. Solar arrays positioned on those peaks can generate power through what would be the lunar night at lower latitudes, interrupted only by brief shadow periods manageable with modest battery reserves. But even polar solar power has limits. The 10% of the year when shadow reaches even the best south polar peaks requires a backup power source. The electricity demands of in-situ resource processing, running the equipment that extracts ice and converts it to propellant, exceed what solar arrays alone can provide at the required scale. Power must be delivered to equipment operating in permanently shadowed craters, where no solar array can function. These demands point toward a power source that operates independently of sunlight, reliably, continuously, and at sufficient output to sustain not just a minimal survival mode outpost, but a productive one. Nuclear fission is the answer that engineering analysis consistently returns to. In 2018, engineers at the NASA Glenn Research Center and Los Alamos National Laboratory completed ground testing of a system called Kilopower in the Nevada desert. The Kilopower reactor used a uranium-235 fission core about the size of a paper towel roll, surrounded by passive heat pipe cooling and connected to Stirling cycle generators that convert heat to electricity. The demonstration unit produced approximately 10 kilowatts of electrical power continuously over the test period, with no consumables, no sunlight, and no moving parts in the core itself. It was the first nuclear fission power system tested in the United States for space applications since the 1960s. 10 kilowatts is a starting point, not a solution. A single crew member on Earth uses roughly 1 kilowatt of power continuously when all domestic consumption is accounted for. A lunar outpost with 4 crew members, life support systems, thermal management equipment, communications hardware, science instruments, and any resource processing capability requires substantially more. The Fission Surface Power Project which builds on the Kilopower demonstration, is targeting units producing approximately 40 kilowatts each. An early outpost would likely require multiple units operating together, with redundancy built in so that a single unit failure does not compromise crew survival. The timeline from the Kilopower demonstration to flight-qualified fission surface power units represents one of the longer development paths in the current program. Hardware must be designed for the specific thermal and radiation environment of the lunar surface, qualified against the vibration and acoustic loads of launch, validated for reliable operation over the years-long lifetimes that a permanent outpost would require, and integrated with the surface power distribution systems, cabling, switching, and storage that turn a reactor into a usable power grid. That work is proceeding. It is not proceeding quickly enough to be ready for the first crewed Artemis landings. It is expected to be a critical component of the later, more permanent phases of surface operations. The Artemis program exists because every attempt before it failed to survive the political environment long enough to produce operational hardware. Understanding what Artemis is, in concrete architectural terms, is essential to understanding whether it has a realistic chance of a different outcome. The architecture looks nothing like Apollo. The Saturn V was a single massive rocket that launched a 3-vehicle stack directly toward the moon. Everything flew together, everything was purpose-built for one mission, and the entire enterprise was under direct government control from propulsion to re-entry. Artemis is a distributed system involving multiple vehicles, multiple contractors, multiple international partners, and commercial companies operating under a different relationship with NASA than anything that existed during the Apollo era. This complexity is not the product of bureaucratic excess. It is the product of engineering reality. The problem is more demanding. The budget is a fraction of what Apollo commanded, and the industrial base that Apollo could draw on no longer exists. The Space Launch System is the heavy lift rocket at the core of the architecture. It is built substantially from hardware derived from the Space Shuttle program. The 4 main engines, designated RS-25s, are direct descendants of the Space Shuttle main engine. The solid rocket boosters flanking the core stage are evolved versions of the shuttle's solid boosters. Using this heritage, hardware reduced the time and cost of early development compared to designing an entirely new vehicle from scratch. It also preserved some of the manufacturing and test infrastructure associated with shuttle-era propulsion systems. The trade-off is cost. NASA's Inspector General has estimated the per-flight cost of the Space Launch System at over $4 billion for early missions, a figure that reflects the vehicle's non-reusable architecture and the overhead costs of a workforce and facility base maintained for low flight rates. Orion is the crew capsule that has survived longer than any other element of the post-Apollo deep space program. Its lineage runs directly back to the Constellation program that Obama cancelled in 2010. The capsule is designed specifically for deep space radiation environments, with shielding and structural margins that the shuttle and the ISS, both operating in low Earth orbit under the partial protection of Earth's magnetic. Its purpose is to serve as a persistent staging platform, a place where crew can transfer between the transit vehicle from Earth and the landing system, descending to the surface, where logistics can be stockpiled between missions, and where science can be conducted without the overhead of a full Earth-to-Moon transit for every rotation. International partners including the European Space Agency, the Japan Aerospace Exploration Agency, and the Canadian Space Agency are contributing hardware to the gateway. Their contributions create the same kind of diplomatic dependency structure that has kept the International Space Station operational across 5 presidential administrations. Then, there is the landing system, and it is where the architecture takes its most dramatic departure from anything that has come before. SpaceX's Starship was selected as the human landing system for the initial crewed Artemis surface missions. The comparison to the lunar module it conceptually replaces requires some adjustment to the imagination. The lunar module stood approximately 6.5 meters tall, with landing gear deployed, and weighed roughly 15 metric tons fully fueled. Starship stands approximately 50 meters tall and weighs over 100 metric tons dry. The scale difference is not incremental. The payload volume that Starship can deliver to the lunar surface could carry habitation equipment, scientific instruments, rovers, resource processing prototypes, and supplies sufficient for surface stays measured in weeks rather than the hours of an Apollo visit. To get there, Starship cannot fly directly from Earth's surface to the Moon on a single launch. It reaches low Earth orbit and then receives multiple deliveries of cryogenic liquid methane and liquid oxygen from tanker variants of the same vehicle, launched separately from the ground. Current planning estimates suggest that between 6 and 16 tanker flights may be required to fully fuel a single lunar Starship before it departs for the Moon. Orbital transfer of cryogenic propellant at that scale has never been demonstrated. Managing propellant that tends to boil off as it absorbs heat in the thermal environment of low Earth orbit across multiple sequential transfer operations, while coordinating a rapid sequence of tanker launches within a window constrained by orbital mechanics, is a challenge that sits at the frontier of what has been operationally proven. It is not theoretically impossible. It has not yet been done. Blue Origin's Blue Moon lander has been selected for later Artemis missions under what NASA calls the Sustaining Lunar Development Contract, introducing a second commercial landing system into the architecture. The competitive redundancy this creates is intentional. A program that depends on a single commercial provider for access to the lunar surface is more vulnerable to that provider's technical or financial difficulties than one with an alternative. Building redundancy into the commercial landing system architecture, while the technologies are still being demonstrated, is the kind of structural decision that distinguishes program design from optimistic assumptions about how well things will go. The architecture that results from all of this is more complex than Apollo. It is also designed for a more complex objective. Complexity is not inherently a weakness. In this case, much of it reflects genuine engineering necessity, genuine international partnership structure, and genuine lessons learned from the programs that came before. Whether it is complex enough to succeed and simple enough to survive the political environment long enough to fly, is the question on which everything else depends. Between the vehicle that delivers the crew to the lunar surface and the surface itself stands one more layer of infrastructure that tends to get overlooked in broader discussions of the program. It is also the most personal. The spacesuit is the boundary between a human body and an environment that will kill it within seconds. Everything else, the habitat, the power systems, the life support, keeps people alive inside a pressurized shell. The spacesuit is what allows them to step outside it. The suits worn during the Apollo missions were extraordinary achievements of their time. They were also designed for a specific and limited purpose, keeping 2 astronauts alive during surface excursions lasting a few hours each, across a mission of a few days total, at equatorial sites chosen in part for their benign thermal conditions. The Apollo suits could not kneel. They could not easily reach the surface. Their mobility was constrained in ways that geological fieldwork on the Moon genuinely suffered from, and they were not designed with any expectation of surviving hundreds of hours of continuous surface operations in the abrasive, dust-laden environment of a South Polar outpost. The development of a new suit for Artemis surface operations began under NASA with a program called the Exploration Extravehicular Mobility Unit, designed from the outset for the South Polar environment, with improved dust resistance, greater lower body flexibility, and the ability to kneel and work close to the ground in ways the Apollo suit could not accommodate. That program encountered cost and schedule difficulties and was ultimately transferred to the commercial sector. Axiom Space, a Houston-based company building commercial space stations, was awarded the contract to develop the suit that Artemis crews will actually wear on the surface, designated the Axiom Extravehicular Mobility Unit. It is the first time in the history of the American human spaceflight program that surface spacesuit development has been handed to a commercial provider rather than managed directly by NASA. Whether that model produces better results than the government-led approach it replaces will become clear when the suit is used in the environment it was designed for. Beyond the suit, surface mobility depends on rovers. The Apollo Lunar Roving Vehicle was a remarkable machine for its time. An open electric buggy that extended the range of Apollo 15, 16, and 17 crews to distances of several kilometers from their landing sites, and transformed the scientific return of those missions. Its direct descendants for Artemis are unpressurized rovers designed for shorter excursions from a fixed habitat, operating across the extreme terrain of the South Polar region with its crater-rimmed slopes, permanently shadowed approaches, and temperature gradients that can change dramatically within short distances. The more transformative mobility concept is the pressurized rover being developed by the Japan Aerospace Exploration Agency as a contribution to the Artemis architecture. The principle is straightforward and its implications are significant. A pressurized cabin means astronauts can travel without wearing suits, seated in a shirt-sleeve environment, covering distances that a suited crew member on foot or in an open buggy could never manage. Preliminary range estimates place the vehicle's capability at approximately 1,000 kilometers on a single charge, sufficient for multi-week traverses that could reach geological targets far from the base habitat and return without resupply. What that kind of range means for lunar science, for exploration, and for the eventual characterization of resources across a wider area of the South Polar region is difficult to overstate. The South Pole is not a single location. It is a region. A rover that can operate continuously across that region for weeks changes what is possible there. Communications infrastructure rounds out the picture of what sustained surface operations actually require. At South Polar latitudes, contact with Earth through direct line-of-sight links is limited by the geometry of the Moon's surface and the positions of ground stations and relay assets. Continuous contact between a surface crew and Earth-based flight controllers, mission support, and emergency medical consultation depends on relay satellites in lunar orbit positioned to maintain coverage at the poles. Closing that gap is part of the Commercial Lunar Payload Services program, with multiple providers developing communication and navigation relay assets as part of the broader robotic precursor campaign. The Intuitive Machines IM-1 mission, which in February 2024 delivered the first American spacecraft to soft land on the Moon since Apollo 17, approached a South Polar site and returned data on surface conditions that feed directly into the planning for crewed operations. Each robotic precursor mission that succeeds adds knowledge. Each one that encounters difficulties adds that too, in a different form. The infrastructure of staying on the Moon is not a single technology. It is a stack of interdependent capabilities, each one necessary, none sufficient alone, all of them still being built. Whether all of that infrastructure ever gets built depends on something that no engineer controls and no rocket can provide. It depends on the political will to sustain a program across the years and decades that building it requires. And the history reviewed across this video does not make optimism easy. But there is a case for cautious confidence, and it is grounded not in hope, but in structure. The International Space Station has been continuously inhabited since November 2000. It has survived the Columbia disaster and the 32-month grounding that followed. It survived the retirement of the Space Shuttle, which required transitioning crew transport entirely to Russian Soyuz vehicles for nearly a decade before American commercial spacecraft took over the role. It survived the geopolitical ruptures between the United States and Russia that in almost any other context would have ended the partnership. As of today, it has sustained unbroken human presence through 5 American presidential administrations and more congressional election cycles than anyone managing the program in its early years could have confidently predicted. How did it survive when every attempt at a lunar program failed? The answer is structural, and it is the template that the Artemis program is explicitly trying to replicate at a larger scale. The station created international dependencies that raised the political cost of cancellation beyond what any single partner was willing to pay unilaterally. When the European Space Agency had built a laboratory module, when the Japan Aerospace Exploration Agency had contributed a research facility, when the Canadian Space Agency had provided the robotic arm that the station's assembly and maintenance operations depend on, walking away from the program meant damaging relationships with allies whose cooperation was needed across dozens of other policy areas simultaneously. No administration was willing to pay that diplomatic price. The station embedded itself in a web of commitments that individual political cycles could not easily unravel. The station also distributed economic benefits broadly enough to create a domestic constituency for its survival. Components were manufactured in multiple states. Operations were managed from centers spread across Texas, Alabama, and Florida. Contracts supported thousands of jobs in communities where aerospace employment was locally significant. Canceling the station meant eliminating those jobs, a political cost that incumbents in affected congressional districts were unwilling to accept, regardless of their party or their views on space policy. And the station produced continuous, visible results. Crews launched on a regular rhythm. Science experiments generated publications and occasionally headlines. Astronauts became public figures who maintained a genuine connection between the program and ordinary citizens through the years when no dramatic milestone was being achieved. The program was never invisible long enough to become abstract. Artemis is attempting to replicate all three of those structural features at lunar scale, and in some respects, it is going further. The Artemis Accords, signed by over 40 nations, establish a shared framework of principles for lunar exploration, including norms around resource extraction, transparency of operations, and conflict avoidance. They are not binding treaties in the formal legal sense. They do not compel signatory nations to fund or participate in any specific mission. What they create is a set of diplomatic expectations, a network of relationships in which American leadership of the lunar return effort is embedded, and a situation in which withdrawal carries costs that extend well beyond the space program itself. When Australia signs the Accords, when Italy signs, when Japan and the United Kingdom and Canada and Brazil sign, they are not just endorsing principles. They are associating themselves with an enterprise whose continuation they now have a diplomatic interest in supporting. The European Service Module dependency on Orion is the most concrete version of this logic. Europe is not a passive participant in Artemis. It is building a critical path component without which the program cannot fly. Severing that relationship requires not just a budget decision in Washington, but a diplomatic rupture with a major ally across every other dimension of the relationship. That is a fundamentally different situation from the Space Exploration Initiative of 1989 or the Constellation Program of 2004, both of which were entirely domestic American efforts that a single administration could cancel without consequences beyond the program itself. The commercial dimension introduces something genuinely new. SpaceX is developing Starship because Starship has commercial applications that exist entirely independently of NASA's lunar program. Satellite launches, point-to-point cargo transport, private spaceflight, the company's own ambitions for Mars. All of these provide motivation for completing the vehicle's development that would persist even if NASA's lunar landing contract were cancelled tomorrow. The fundamental technology for lunar access is, for the first time in history, being developed by a company with its own reasons to build it. That partial decoupling from the political cycle is a structural resilience that no government-only program can replicate. Then there is China. The China National Space Administration has demonstrated genuine technical capability across its Chang'e program. Chang'e 4 landed on the far side of the Moon in January 2019, the first spacecraft in history to do so, operating through a relay satellite positioned at the second Earth-Moon Lagrange point to maintain communications with a surface that has no direct line of sight to Earth. Chang'e 5 returned lunar samples to Earth in December 2020, the first sample return mission since the Soviet lunar program ended in the 1970s. China has declared its intention to land crew on the Moon by approximately 2030 and is developing the International Lunar Research Station in partnership with Russia as a long-term surface presence program. This competitive pressure is the most reliable political motivator in the history of the space program. It was fear of Soviet capability that produced Apollo. Concern about Chinese capability is providing the bipartisan congressional support that Artemis currently enjoys, the unusual alignment across party lines that every previous post-Apollo lunar program lacked. That alignment may not persist indefinitely, but while it holds, it provides the political foundation without which no amount of engineering excellence can sustain a program. The risk in the competitive framing is worth naming directly. If Lunar Return becomes primarily a race to arrive before China, rather than a project to build something permanent, the same sprint-then-collapse dynamic that ended Apollo becomes possible again. Arriving at the South Pole first, with an architecture designed for a single dramatic landing, and no infrastructure capable of sustaining what comes after, would be a victory as hollow as it would be brief. The lesson of Apollo is not that the first landing does not matter. It is that the first landing is where the real work begins, and that beginning it without the architecture to sustain it is a way of ending rather than starting. The structural conditions for a durable program are more favorable now than at any point since 1972. That is not a guarantee. It is a reason to take the attempt seriously. Underneath the engineering challenges and the political ones, there is a layer of the Lunar Return story that receives almost no attention in popular discussion. It concerns the question of who owns what happens on the Moon once humans are there in numbers, operating equipment, extracting resources, and competing for the most strategically valuable locations on the surface. It is a question with no agreed answer. And the window for establishing one is closing faster than most people realize. The foundational legal document governing human activity beyond Earth is the Outer Space Treaty of 1967. It was negotiated during the height of the space race, ratified by all major spacefaring nations, and remains the cornerstone of international space law. Its core provision is clear: no nation may claim sovereignty over the Moon, over Mars, over any celestial body. The Moon belongs to no one. No flag planted there, no matter how many missions or how much infrastructure a nation places on the surface, constitutes a territorial claim that international law recognizes. That principle is broadly accepted and not seriously challenged. Where the treaty becomes complicated is the question it does not answer. It is silent on resource extraction. Whether a nation or a company that mines water ice from a permanently shadowed crater and converts it into propellant has appropriated a portion of the Moon in the sense the treaty was designed to prohibit is genuinely contested. One reading holds that the treaty prohibits any such extraction, that the Moon's resources are a common heritage of humanity that cannot be claimed by any individual actor. A competing reading holds that the treaty prohibits sovereignty claims, but says nothing about use, that extracting resources from a shared commons is no different in principle from fishing in international waters, where the act of taking fish does not constitute a claim over the ocean itself. The United States has, through domestic legislation, aligned itself firmly with the second interpretation. The Commercial Space Launch Competitiveness Act of 2015 explicitly asserts that American citizens and companies engaged in commercial recovery of space resources are entitled to own, transport, use, and sell those resources. It is a unilateral declaration, made without international negotiation, that other spacefaring nations have received with varying degrees of skepticism. Luxembourg passed similar legislation 2 years later. The Artemis Accords, in their treatment of resource extraction, advance the same position. Extraction is permissible, transparency is expected, and operational zones around active sites should be respected. China and Russia have not signed the Artemis Accords. They are developing the International Lunar Research Station under a separate framework that operates outside the Accord's normative structure entirely. Two parallel governance architectures for lunar operations now exist, with no agreed mechanism for resolving conflicts between them. Here is where the geography of the South Pole makes the legal uncertainty acute. The peaks of eternal light that make sustained solar-powered operations viable, and the permanently shadowed craters that hold the water ice that makes the economics of deep space exploration transformable, occupy a relatively small area near the South Pole. The most favorable sites, those that combine near-continuous solar illumination with proximity to confirmed ice deposits, are limited in number. If two crewed programs from different nations, operating under different legal frameworks and with different conceptions of what the Outer Space Treaty permits, both target the same ridge or the same crater rim, there is currently no established process for resolving the conflict. Frans van der Dunk, a space law scholar at the University of Nebraska, has written extensively on the inadequacy of the existing framework for governing the kind of resource-competitive operations that South Polar activities will generate. The United Nations Committee on the Peaceful Uses of Outer Space has debated aspects of resource law for years without producing binding norms. The Antarctic Treaty System, which has managed competing territorial claims and scientific operations on the most analogous environment on Earth through a framework of cooperative governance, took years to negotiate and was possible in part because Antarctica has no resources of immediate commercial value. The Moon, if water ice extraction becomes operational at scale, will not have that luxury. The philosophical question beneath the legal one is worth sitting with because it does not resolve easily. Do the resources of other worlds belong to the nations and companies capable of reaching them first, or to humanity as a whole? The first answer rewards investment, capability, and risk-taking. It creates incentives for the private capital that has already transformed launch costs and will likely do the same for surface operations. The second answer reflects a view of the cosmos as a commons that belongs to everyone who has ever looked up and wondered, including the billions of people on Earth whose nations have no space program and no prospect of one. Both answers contain something true. Neither contains the whole truth. And the absence of an agreed framework for navigating the tension between them is not an abstract problem. It is a practical one that becomes more urgent with every mission that approaches the South Pole. Step back from the engineering, the politics, the law, and the competing programs, and what remains is the question this video started with, restated now with everything that has been laid out behind it. Why have we not gone back? The full answer, assembled from everything examined across this video, is this. Apollo was not a capability that humanity developed, demonstrated, and chose not to use again. It was a singularity, a convergence of geopolitical terror, unconstrained funding, industrial mobilization on a wartime scale, and a tolerance for risk that democratic societies cannot reconstruct in ordinary times. When the conditions that produced it dissolved, the capability dissolved with them. What was left behind was not a foundation, it was a memory. The 50 years that followed were not a failure of nerve. They were a return to the conditions that prevail when existential fear is absent, which is to say, ordinary conditions, in which extraordinary things are extraordinarily difficult to sustain. Multiple attempts were made, each consumed resources and produced partial progress. Each was cancelled when political cycles turned and institutional patience ran out. Each cancellation left the next attempt starting from a position worse than the one before, with more scar tissue, more dispersed expertise, and a workforce increasingly conditioned to treat deep space commitments as temporary, and yet the attempt continues. The Artemis program is more structurally resilient than any of its predecessors. Its international dependencies are real and consequential. Its commercial components are being built by companies with independent reasons to complete them. Its competitive geopolitical context is providing the political motivation that scientific arguments alone have never reliably generated. The robotic missions arriving at the lunar surface in advance of crew are building knowledge rather than just spending money. The pieces, for the first time since 1972, are assembling in a way that looks less like the beginning of another cycle and more like the beginning of something that might actually last. The first Artemis crewed landing, whenever it comes, will not be the culmination of this story. That is the deepest lesson Apollo teaches, and it is the lesson most often ignored. The moment a crew descends to the South Polar surface and the world watches will be extraordinary. It will feel like an arrival. It will actually be a beginning. The years and decades that follow that first landing will determine whether it becomes another magnificent dead end or the start of something permanent. A habitat tested in the actual environment. A power unit deployed and validated through a full cycle of lunar day and night. An ice extraction experiment conducted in a permanently shadowed crater. A crew rotation completed, and then another. each one unremarkable compared to the first landing, each one more important. That is how civilizations build things that last, not in single dramatic moments of arrival, but in the sustained, patient, often invisible accumulation of capability. The transcontinental railways were not completed in the ceremony at Promontory Summit when the golden spike was driven. They were completed in the years of subsequent track laying, bridge building, and operational experience that turned a demonstration into infrastructure. The same logic applies here, on a scale that has no terrestrial parallel. Humanity has never established a permanent presence on any world other than this one. The International Space Station is as close as we have come, and it orbits at an altitude a high-altitude aircraft could theoretically reach, perpetually within hours of emergency return. Whatever comes next will be further away, more exposed, more demanding of every system and every person involved, and more dependent on the kind of institutional commitment that human history suggests is genuinely difficult to maintain across generations. Whether we can supply that commitment is not an engineering question. It is not a question that any rocket or habitat or legal framework can answer. It is a question about what kind of civilization we are and what kind we are capable of becoming. The Moon is 384,000 kilometers away. It has always been 384,000 kilometers away. The distance that separates us from a permanent presence there is not measured in kilometers at all. It is measured in the political will to sustain funding through transitions of power, in the industrial commitment to develop hardware across decades rather than years, in the international cooperation required to share costs and risks across borders, and in the institutional patience to absorb setbacks without abandoning the objective. Gene Cernan's footprints are still in the dust at Taurus Littrow. They will be there for 1,000,000 years, as sharp and clear as the day he made them. The Moon does not care whether we return in 5 years or 50. It has been waiting 4.5 billion years already. The question has never been whether the Moon is reachable. We answered that in 1969. The question, the only one that has ever really mattered, is whether we are the kind of species that finishes what it starts. We do not yet know the answer, but we are closer to finding out than we have been at any point in the last 50 years.